Today we are going to be talking about determinants and inverse matrices. By the end of this video, you should be able to evaluate a 2x2 and a 3x3 determinant, and you should be able to find the inverse of a 2x2 matrix. First, a determinant is a value of a square matrix. Please note that you can only find the determinant of a square matrix. The determinant helps you determine whether or not a matrix has an inverse, and we'll get to that later in the notes. To find the determinant of a 2x2 matrix, if we have matrix A with elements A, B, and C, D, there are a couple ways you can see the notation for determinants. Sometimes you will see DET A, meaning the determinant of matrix A, and sometimes you will see the determinant written with kind of like absolute value bars instead of square brackets. And that means that you are finding the determinant of that matrix. To find the determinant of a 2x2 matrix, you are going to multiply A times D and then subtract the product of B and C. So you do the product of this minus the product of that. So let's look at a couple determinants. We want to find the determinant of this first matrix. We have 4, 2, -3, and -5. So we want to find the product of A and D. So 4 times -5, and subtract the product of 2 and -3. So we get -20 minus -6. So -20 plus 6 is -14. And your determinant should always just be a number. If we look at the second example, we want to find the determinant of this matrix. We are going to multiply A times D, 9 times 6, and then subtract 15 times 2. So we get 54 minus 30, which is 24. That's how we find the determinant of a 2x2 matrix. To find the determinant of a 3x3 matrix, it's a little bit more complicated. We use a process called expansion by minors. To start with, we are going to look at our matrix, and I'm going to pick one row or one column to use as scalar values. For this example here, I'm using the first row as our scalar values. Then you need to assign all of the numbers, positives and negatives. This does not change the value of the number in the matrix. It only affects the scalar values, which I'll show you in a minute. The number in the top left-hand corner will always be positive, and then you are going to alternate positive and negative as you go through the matrix. So, if I'm starting with A1 as my first scalar, since this was assigned a positive value, then I'm going to keep the sign of A1. Then I'm going to cross out the row and the column that A1 is in, and I'm left with 4 values, B2, B3, C2, and C3. And I'm going to take those 4 values, and that will become this smaller matrix here. And I need to find the determinant of that smaller 2x2 matrix. Then I continue across my row. I have A2, and I assigned that negative, so I'm going to have minus A2. If I cross out the row and the column that A2 are in, I'm left with B1, B3, C1, and C3. So I'm going to write that as a smaller 2x2 matrix. So I need to find the determinant of that and multiply by negative a2. Then lastly, if I continue along this first row that I chose, I have a3, and I assigned that a positive, so I have plus a3. And then if I cross out the row in the column that a3 is in, I'm left with b1, b2, c1, and c2 as my smaller 2 by 2 matrix. So this is the algorithm for finding the determinant of a 3 by 3 matrix using expansion by minors. Let's take a look at a couple of examples with numbers so you can see how this works. Now, you can choose any row or column that you want. Generally, rows or columns that contain the number 0 are going to be preferable because it's going to reduce the amount of work that you need to do. So in example number 3, I'm going to choose the third column as my scalar values. Then I'm going to assign the positives and negatives for this matrix. So I'm going to start with the first term in this column, which is negative 1. Since that has a positive, I'm not going to change the sign. If I cross out the row and column, then I'm going to have this smaller matrix with 1, 1, 2, and negative 3. The second term in the third column is 0, so that makes my life easier. I don't have to do the calculation because I'm going to end up multiplying by 0. Then the third term is 5, and I assign that a positive value, so I'm going to keep that as plus 5. If I cross out the row and the column, I'm left with the smaller matrix 4, 2, 1, 1. I have negative 1 times the determinant here. So 1 times negative 3 minus 1 times 2. Minus 0 plus 5 times the determinant here. 4 times 1 minus 2 times 1. So I get negative 1 times negative 3 minus 2 is negative 5, plus 5 times 4 minus 2, which is 2. So I get 5 plus 10, which is 15. You'll notice that problem number 4 is the exact same matrix. But instead of choosing the third column as my scalar values, I'm going to choose the second row. And we should still get the same determinant regardless of which row or column you choose. So I'm going to go ahead and assign my pluses and minuses. To start with, my first value in this row is 1. Since I assigned this a negative, I'm going to change it to a negative 1. If I block out that row and column, I have 2, negative 1, negative 3, 5. Then the next value in my row is 1. It's assigned a positive, so I'm going to have plus 1. If I block out that row and column, I have 4, negative 1, 2, 5. And then the last value in that row is 0. So I don't have to do anything else with that. So now I need to find the determinant of these matrices. I have 10 minus 3 20 minus negative 2 and minus 0. So I have negative 1 times 7 plus 1 times 22. So negative 7 plus 22, which is 15. So regardless of which row or column you choose for your scalar values, you should get the same determinant. Next, let's take a look at the inverse of 2 by 2 matrices. In general, an n by n matrix, so square matrix, A, has an inverse if and only if the determinant is not equal to 0. Today we're only going to worry about finding the inverse of a 2 by 2 matrix. And to do that, the inverse matrix, which is represented by this symbol, a to the negative 1 power, or A inverse, you do 1 over the determinant of A as a scalar value, and then you rearrange your matrix a little. You are going to switch A and D, and then make B and C negative. Let's take a look at an example. If we want to find the inverse, B inverse, of the matrix B, we need to first find the determinant. The determinant of B will be 20 minus negative 6, or 26. So the inverse matrix will be 1 over 26 times, we need to switch A and D, so switch 5 and 4, and change the signs of B and C. So we will have positive 3 and negative 2. The last thing we need to do is just multiply by our scalar value. So 4 times 1 over 26 gives us 2 over 13. 3 times 1 over 26 is just 3 over 26. Negative 2 times 1 over 26 is negative 1 over 13. And 5 times 1 over 26 is 5 over 26. So that is our inverse. Inverse matrices are not always the prettiest. Sometimes they have fractions, but that's okay.